Okay. Previously, we talked about noise conditional score matching score networks. What was the idea there? What was the idea in score in noise conditional score networks? The problem was there was three problems. Two of them appear in the training part. The first one was the manifold hypothesis. The second one was the inaccuracy of inaccurate estimations in low density regions. And one of the most important point was the slow mixing of Langevin dynamics. What was the problem there? Assume, for example, I have the mixture of these two Gaussians. If I start with, for example, uniform samples in the space, for example, uniform in this area, at the end of the day, I will have a almost similar number of examples here and here. This was the problem with slow mixing. Okay, but we see that if we start with a noisier version of the data, we know that then we talk about how if you add noise to this mixture of Gaussian, we know that just the variance of the noise is added to each component. Okay, so as a result, if I add noise to this mixture, I have something like this. Sorry, I will have for a high level of noise. Okay, something where each peak is more near to this component than this one. So when you start generating samples from this distribution, then much of your samples will go toward the peak region of this component. Okay, here. All the samples you generated before, they were uniformly generated, but when you use the score function of this Gaussian component, which is the mixture of these two with high level of noise, as a result, all the samples will gather in the peak area of this component. We know that this is two components, but because the variance is very high, we see them as one component. What happened next? Because the position of this peak is nearer to this part, and the rate of this distance with respect to this distance is based on the mixing ratio of these two components. For example, this one is 1/3, this one is 2/3. As a result, when you start, now you use these samples as the initialized samples for a lower version of the dataset, for a lower, noisier version of the dataset. For example, this one. This is a lower, noisier version. What happened? Also, you have a lower peak here. What happened? A larger number of samples will go to this direction, and a smaller ratio go to the other one. And if you continue, at the end of the day, you have samples almost similar to their mixing ratio in both regions. This was the way adding noise solved the problem. Okay. Now, in the noise condition score networks, what happened? We have several levels of noise. At the end, we have sigma. This is the least noisy version, and this is the most noisy version. And what happened? We start with random noise. We start with the sample from Gaussian distribution, for example, XL, and denoise it using each level of the noise we have in our training procedure. And at the end, when using the last one, because this one is correspond to the least noisy version of your data set, you have almost something from your own data set, and the result will be a understandable image. But here still we have some problems. What is that problem? The problem is that the noisiest version is not maybe is not familiar with the pure noise. Okay. As a result, we want to cover this gap in the diffusion models. We want to add other levels of noise in this gap, and at the end of the day, we want to exactly model at the end. For example, this is the last, I call it T. This is the last level of noise I add. I want to see exactly this, the pure noise. What happened? We add the noise to the data set in different levels. During the noise condition score matching, we have a maximum level of noise, which was this one. But we know that even at this level of noise, you have some intuition from the main content of the image. Now I want to rigorously continue this path and add noise until I reach a point that the content of the image is completely cleared or missed from your signal, and start to denoise that version. It means starting from complete noise, pure noise, and recover my data. This is the objective in diffusion models. It means that they are an extension to some extent to noise condition score networks. Noise conditional score networks. So, but the intuition is completely different. We start with intuition here. We start with variational learning. So, what is the intuition? We know that in noise conditional score network, we have something like this. You start with x0 and generate different levels of different noisier version of your data. For example, here I just assume 3 different level of noise. Okay. What happened? I have this image. I form this distribution, sample from this distribution, and reach this new image, which is a noisier version. I continue this procedure until the end. Just pay attention to the fact that I reverse the indexing. We generally, in the noise condition networks, we generally have the higher index means lower noise, but here it's the reverse because it is aligned with diffusion models. Okay, just pay attention to the fact that I reverse the indexing. Sigma 1 is the smallest and sigma 3 is the largest, just to be aligned with diffusion models. So, you know, at the end of my sampling, I have something that you clearly observe the dog inside this image. So the content is not missed yet, even at the noisier version of your data. Okay? Then, during the generation, what happened? You start with a completely, with a sample from a pure noise, this one, and use T steps of ALDA, Anil-Langevin dynamic algorithm, with this value of the score function with the noisier version, with the noisiest version, to generate some samples from this distribution. This is one inner loop of Langevin, Anil-Langevin. This is just one inner loop. We have 2 loops, one inner loop, one outer loop. The outer loop iterate over the noise variances. The inner loop just is the Langevin algorithm. So I start with a pure noise. I use T steps of ALDA. I reach this image, and then I continue this procedure just with the newer version of sigma. The previous one was sigma 3. It means that I want to recover something from the noisiest version of my data. Why? Because because we know that S theta of x and sigma 3 is the score function of q sigma 3 of x tilde, the noisiest version. This is the score function for the distribution of the noisiest version of your dataset. So at the end, you have samples from this distribution, and we know that this is a very expanded version of your dataset because you add a high level of noise to your original dataset. Any question? I continue this procedure. Then I use the resulting image in the previous part as the input to ALDA again, then the next inner loop. And denoise it using a set of x and sigma 2. What happened, I transfer from this distribution to this new distribution, x2 of x tilde. And I know that this is nearer in terms of noise added to your true data distribution. And you see it visually here. The diag image is becoming more and more clear. This is, yes?
Is this the training process?
No, this is the sampling process. During the training, what happened? You start with, you sample one x, and then use this loss, score denoising, score matching with sigma I. Use a summation of these loss, lambda of sigma I, and this summation. During the training, we use this loss. For example, we sample this dog, then generate different noisier version. Generally, we do not sample one dog. We sample L samples from the training data, x1, for example, x2, xl, and we take a noisier version of for each of them, x1 tilde, x2 tilde, xl tilde, and use each of these pairs to estimate one of these losses to have diversity. But you can easily use just one sample at different level of noise and then use it for training. This is the sampling procedure. I start from pure noise and use ALDA to denoise it, to generate a sample from the true data distribution, okay? And if I continue at the end, I have something like the true data, samples from the true data. But the problem is that you can better model this part, you know? If you continue your noise addition process for more than, for example, these 3 times, you can model better this gap. You have, for example, instead of 3 levels, you may have lots of levels here to gradually add the complexity of forming data. This is the idea in diffusion models, okay? So, noise condition score network train a model to learn the score function for noisy data for several levels of noise to solve these 3 problems. The first 2 are very severe during the training. The last one is during the sampling or generation. But the point is that in NCSN, in the noisiest version, in the most noisy case, the input X is almost buried with noise, but there is still X information in the noise input. What do I mean here? Indeed, this is the noisiest version. This is not. This is for generation, okay? During the training, we just have used this one. Using this one, you see the noise, you are observing the content. It is not, the content is not completely buried in the noise. This is the change. This is the point that will be changed for diffusion models. Okay. Clear everything? Okay. But what is the diffusion probabilistic models? In diffusion probabilistic models, we add noise to the input in a Markov chain model. It is not important the name. We will see that it is a very simple model to add noise to your data. And we reach a pure standard Gaussian noise. It means that we continue the process of adding noise, but there is a point. We reach standard Gaussian. It means that you add noise so that at the end you have standard, sample from standard Gaussian, not arbitrary Gaussian with different, for example, covariance matrix. We see how we can add noise so that at the end we have standard Gaussian sample. So now assume that you can train a model that can estimate the score function for different noise levels. Then starting from pure standard Gaussian noise, we can progressively denoise the input using the trained model and finally generate a sample from the data distribution. Thus, we have a generative model. So it means that we just want to add other steps in between so that in the noise addition process, at the end, we have exactly pure noise and start to denoise that one. This is completely aligned with our generation, because our generation starts from pure noise. Okay? This is what we will cover in the diffusion models. We will talk about variational diffusion models, but there are other approaches for diffusion models. You can follow them. But because this one is aligned with our intuition of elbow, this is a great option to be discussed here. Okay. We are all familiar with variational autoencoder. This is a very simple, this is symbolic of VAE. What happened? We have X. We go to Z space using approximate posterior. We are all familiar with this Q phi of Z given X. And then there is, which is called encoder. And then using this conditional, we can return to the original space. This is the decoder. And this is our model. This is our generative model. We know that if you do not have the encoder, it's not a problem. We can generate samples by sampling from Z from the prior, using this function as the transformation, and then we have samples from the observed space. This is just autoencoder. What?
The one that you mentioned earlier to add noise and then denoise it.
Yes.
So is this used for training?
During the training, you generate noisy version of data and learn the model to
Denoise it.
Yeah. For noise condition score function, we just continue this procedure for limited number of steps. And at the last and the noisier version, you still have the content of your data in the noisy data. Okay? But in diffusion model, we want something else. We want in the noisier version, you have a standard Gaussian, which is not, you do not have anything from your data.
So the slide that showed that you had the picture of a dog and then propagated to generate the noise. This is for the training.
This part is training. For this generation, I start from Okay. This is autoencoder. In VAE, the evidence or observation log likelihood, you know what is evidence, is lower bounded as this function elbow, and we know that elbow is defined as the expectation over Z coming from the approximate posterior of the log of the joint over the approximate posterior. This is the elbow, nothing more, just elbow. And we can replace this Q phi of Z with any distribution you want. Still you have a lower one, but the lower one is not tight. The problem is the tightness. This is the lowest. If this is a good approximation to the true posterior, if that's the good approximation to this function, this is a tight one, lower one. So do not focus on the encoder, okay? And we can change it like this, as we see before, and we generally assume that the prior distribution over the latent has no parameter like this one. But you can, in the general form, assume that the prior is also parametric. So now pay attention to this fact. I want to have several VAE stacked together. Pay attention. I have this VAE. You can train it and you can do anything with it. Okay. At the end of the day, for each X, you can have a Z1 here. Now I can apply another VAE over the new latent space. I want to apply a new variational autoencoder over my latent space. It means that you have a VAE, but it is not in your observed space. It is in your latent space. For simplification, assume that in the first step, I design this completely. We know how to design it. and transfer each of the data here using the approximate posterior here and replace it with the mean value. With the mean value of that Gaussian that this function generates for you, replace it with the mean. So each data has a corresponding new vector. Does it make sense? Now you have a new space, you have a new data set, and it is completely vectors. It is not probabilistic. You can design another VAE over that space. And continue this procedure for t different times. Different latent space are captured with another VAE. But the problem is that you cannot assume that this here you have X, here you have exactly samples. You should look at this procedure in a probabilistic way. But how we can look at that? One simple approach is to assume that all of these latent space are gathered here. All of them together are gathered here. And you have this VAE. This is exactly VAE, but the dimension of the latent space, all the latent variables are here. We know that they are interconnected. But it is not important, because when you have the joint, it means that any kind of interconnection is possible. You have the joint. You talk about the joint. You do not know how they are interconnected, but they can easily be interconnected. So I put them together here. All of them, pay attention to this bit. All of them are here, and they are internally interconnected. But the important point is that if you look at this way, you have again a VAE. And this VAE can easily be formulated and can be easily learned, because it is aligned with your previous intuition to VAE. So what happened? Now I want to design the encoder and decoder. The encoder is the approximate posterior over the latent. The latent was previously 1z vector, now it's t different vectors. So I need to have a distribution over all of them given x. This is the approximate posterior. Just we extend, nothing more. And also the model is, if you have all the latent, then you can give a distribution over what you observe. Just if you replace this 1 to t with for example 1, you have a simple VA. This is called hierarchical variational autoencoder. So we have a hierarchy of VAEs, and we know that we can simplify them as this formulation and visualization. This is just nothing. Now we want to talk about the lower bound in this new word. This word that we have t different vectors, random vectors in our latent space. So nothing changed, because you have elbow and you have a distribution, you have an approximate distribution over all the vectors given what you observe, and this is exactly the ratio of the joint of what you observe and all the latent space, complete latent space, or the approximate posterior. Just replacing in the elbow this approximate posterior with q phi of z1 to t given x. Okay? Is everything clear now? Yes.
So what's the format of the joint? Are they like concatenated or?
No. That's not a simple concatenation. They are exactly a VAE on top of each other. But you can look at them this way. Why? Because when you talk about the joint, it means that the internal connection is free. They can have any type of internal connection, and we know that they have this type of connection with each other. Yeah. So, but we talk about this. This is the most free formulation. Why? Because you talk about the joint here. The joint can be any type of relation between the, you may have something like this. When you talk about the joint, okay? Assume this X, this is Z1, this is Z2, this is Z, for example, 3 until ZT. We have lots of samples. For our model, we know that they are connected in this way. What does this arrow mean? This arrow means that the information from Z are coming to the Z1, are coming to Z2, and then Z3 have lower information than Z2. Z2 has a direct connection to Z1. So the most complete set of information about Z1 is captured using Z2. But Z3 has lower information about Z1 than Z2. Why? Because it is not directly connected. This is what this Markov chain applies to your model. Okay? But when you use something like that, because the joint can be connected in any way. For example, Z1 can be connected to here, to all of them. If this is the case, still that formulation works because you have the joint. The joint is complete freedom. But we know that our problem is not the joint. And these arrows have meanings. These arrows have meanings. What is the meaning of this arrow? This is very important to understand. What is the meaning of the why? If we do not have an arrow from 1 to t, what happened in the joint formulation? This is the most important point to understand here. This arrows means that zt, for an arbitrary t, is independent of let me see what's... Oh, zt condition on zt minus 1 is independent of the previous z's. This is the important point to understand here, okay? Let me talk about this formulation. This is the direct consequence of our Markov chain relation, okay? This is z1, this is z2. For example, this is z3 until z big T. For example, I select T to be 2. No, let me talk about Z3. Z3, I select T to be 3. Z3 is a condition on Z2 is independent of Z1. Does it make sense for you? It means that if you have Z2, you have the most informative, you have the most information about Z3 because they have an indirect connection. And Z1 is connected to Z3 through Z2 and the previous ones if you are in the upper level of the chain. Okay? This is the important point. So this connection has this consequence. These types of arrows, the arrows are not arbitrary, they are sequential. Z1 is just connected to Z2, Z2 to Z3 until the end. For the general case, if you are at level T and you are given the previous random vector, then you are independent from all the previous ones other than T minus 1. This is the most important point here. Is it clear for all of you why this happened? Yeah. So, as a result, we have P of Zt given Zt plus 1 to Zt, let me check it. Zt, oh, this is a problem with me. I write down the future. Yeah, I will correct it. Do not pay attention to that part. This part, will clear this part for the moment. Look at this one. I know that my approximate posterior must give me a distribution over the joint given x, okay? And I know that this joint can be written as, using the chain rule, can be written as the distribution over the first one given the condition is fixed. The distribution over the second given the condition and the first one, the distribution over the t given the previous ones, and x until the end. So what is my simplification here? Here I do not have any simplification because z1 and x are connected with directly. z2 given x and z1. z2 given x and z1. What happened? z2 has a direct connection to z1. If you have z1, you have all the information about the z2. X is not needed anymore. So z2 given z1 and x equals z2 given z1. Is it clear? This is the result of arrows and the Markov chain property. Okay? If you continue this procedure, all of them will be simplified. And you will not have x in the, just you have x in the first one. From the second to the L, you do not have x. You are building hierarchy of VAEs. Okay? If you are at the first level, x is important. But if you are at the second level, the previous latent is the most informative information. X is not informative with respect to the previous level anymore. So, is it clear for all of you what happened here? Yes.
Is this notation for simplification, or this is what actually is happening?
What actually happened? Yeah.
So, for example, in Z2, Z1 still has some information about X.
Z1, the information, you know, we are talking about Z2. Who is more informative about Z2, Z1 or X? Is there any information that X have access to about Z2, but Z1 has no access? So we can simplify as this. I put aside X. Clear? Very important, this point. Okay, we simplify the joint, the approximate posterior, the conditional approximate posterior, using the Markov property. So I can simply write this joint as a factorization of those parts. Also, we have these arrows in the decoder. How can I use them? These arrows, let me see this one, ZT. Yeah, this is correct here, but in the previous slide it was not correct. Okay, I will correct it and update. What happened here? We are in the decoder part. Again, put aside, we are talking about the approximate posterior or the model itself. We are talking about the distribution. And this distribution has this property. How can I simplify? How can I use that arrows for simplification? But based on those arrows, we know that ZT is independent of the Z higher, is independent of the higher index given its next one, okay? If I am at this step, Z1 is independent of what is previous Z2 if you have access to Z2. Completely similar to the previous one. We are talking about the distribution. We are not talking about the approximate posterior or the model itself. We are talking about distribution and just the direction of the arrows changed. So we just, previously ZT was independent of its past, now it's independent of its future, if you interpret indexes at time sequence. Is it clear how we derive this formulation, this independence? Okay. And also, this is the important point. If you want to observe what you need, X, and you have access to Z1, the other latent variables are not important. Very important. If you want to observe something, if you want to have your distribution over what you observe, if you have Z1, the lowest, I don't know what to call it, the lowest level in your hierarchy, okay? If you have access to Z1, Z2 until the Z and ZT are not needed anymore. You can only use Z1 to infer what is X. This is very important. To understand what you observe, you just need to have Z1. As a result, the joint is another part in elbow. This is the denominator in elbow, okay? The joint can be written as this one. The joint can be the model distribution over ZT. The model distribution over ZT minus 1 given ZT until the end. I start the chain using end. The joint can be the distribution of the end, the distribution of ZT minus 1 given the end until the end. Okay? What happened? How we can use the independence here? This one is not important, this one is not important. Here. The distribution of ZT given the next latent in the hierarchy. We know that if you have ZT plus 1, ZT plus 2 until Z uppercase T are not important. So I can simplify this term as here. Does it make sense? Exactly similar to the previous property. So, based on the connections, or in other words, based on the Markov property, I can simplify the conditional approximate posterior as this one, and also simplify the joint as this one. Do you agree with me? Okay. So I can rewrite elbow for the complete hierarchy as this formulation. It means that expectation over the joint conditional approximate of the joints or the conditional approximate. This is just elbow, just we use the Markov property. Now we want to switch to variational diffusion models. What we talk about is the formulation of hierarchical VAEs. This is just Markovian hierarchical VAEs. It is hierarchical because it has hierarchy of VAEs. It is Markovian because the connections are as we observed in the previous slides. Okay? So they called Markovian hierarchical VAEs. Now we want to switch to variational diffusion models, and see how they can be extended and they can be simplified, because variational diffusion models are a special family of hierarchical VAEs. Okay. So how we can switch from Markovian hierarchical VAE to variational diffusion models? Assume we have a Markovian hierarchical VAE with the following restrictions. Pay attention to these restrictions, then we use them to simplify the notation more. The first simplification, the first restriction is that each latent vector ZT is of the same dimension as X. This is not necessary for VAE or hierarchical VAE. You can select the latent space much lower than what you observe. The dimension of the latent space much lower than the observation space, okay? But here, we assume that the dimension of the latent space, all the latent spaces, Z1, Z2, ZT, is exactly similar to your X. This is one restriction, okay? Second, pay attention to this second. It may be a bit strange, but it is very interesting property. The encoder is not a parametric function. It is a predefined linear Gaussian model. It is not trainable anymore, in contrast to vanilla VAE. This is very important to understand and capture the concept, okay? I mean, I do not want the encoder part to be learned. I just select something for the encoding. But the selection is intelligent, okay? The selection is a linear Gaussian model. You will see that how it can be used to develop a generative model. This is the critical point, that at the end provide you with a generative model. What? You do not need to learn the encoder. The encoder is selected. We know that any encoder, we have VAE. We have elbow. Because elbow is independent of what you select as your approximate posterior. It is always a lower bound. So you select something, and then you train your model to maximize elbow. We talk about this more. Just pay attention to the fact that you select the encoder. It is strange. It is a bit strange. The encoder is designed such that the distribution over the last latent vector zt is a standard Gaussian. This is exactly the result of your second property. You design encoder so that the last latent vector zt is a standard Gaussian. X, z1 until zt. We know that you do not learn the encoder part anymore. So these transformations, these transitions are not learnable anymore. They are fixed. Because they are fixed, you can design it so that the last latent is standard Gaussian. Very important. We will see why this property is important. So, if it was learnable, you do not have any guarantee. At the end of the day, you have no standard Gaussian here. Or maybe you should impose very complex property to your model so that you guarantee that the last one is Gaussian. But here, you use one fixed transformation, and that transformation guarantees that the last one is a standard Gaussian. Why do we need the last one to be a standard Gaussian? Exactly. Because of sampling. In the sampling, we start from a standard Gaussian. And if the model can provide the same thing, it means that you are, in the generation, you are completely aligned with your training. Because during the training, you learn to decode from the pure Gaussian. Now you are at the space that you generate exactly aligned with your training procedure. Does it make sense? Okay, so pay attention to these three very important property of the VDM. The first one, the dimension. The second one, the fixed encoding, and the last one is the distribution over the last. Right.
I'm confused. I thought X was the source image.
Yeah, X is the source image.
I'm confused, but what is visible random vector X?
X?
Equals the visible random vector X image.
Yeah, it means that the latent space, for example, if you are working with 32 by 32 images, the latent space are also 32 by 32. Yeah. Something like the flu models. In flu models, we have the same dimension in the latent. Here also, we have the same dimension. Okay, pay attention to these three. They are all used during our discussion. So, what happened? No, based on this restriction, I want to update our formulation and notation and this one. Okay? Yes.
And the encoding part is like vertical functions, right?
Which one?
The encoder.
No, it is not invertible. It is a probabilistic transformation. The probabilistic transformation cannot be inverted. Okay? But it is fixed. Okay? Think of this point, okay? I have elbow of x and theta and phi. Now I miss phi because the encoder is not trainable anymore. It is fixed. It is not parametric. It has not any parameter. What happened if I maximize this elbow with respect to theta? Where I have the maximum of elbow, it's the place that the posterior over the latent t given x equals that fixed distribution. This is what happened in practice. It means that your model understands how to reverse it in probabilistic sense. It is not a transformation like flu models that you can easily invert it. Okay? Transformation in VAE is invertible, you can easily invert it. It is something like this. The model understands how to invert it at the end of the day. We will talk about this topic more. Any question? I want to use the restrictions to update my notation and formulations. Okay? The first one, we talk about this x, z1, z2, z3. What happened next? Because they are all of the same dimension, I use x for all of them. Pay attention. This x1 changes to x0. It means that what you observe is x0, index 0. Z1 transforms to x1, x2, xt. This is the notation generally used for diffusion. Just a change of notation. Okay? Why? Because we know that all x's are of the same dimension, Rd. But this x0 is the observed, xt is the last. Yes.
Also, like z there, they can all be used to do like representation learning. So they just completely
Yeah.
Because they are of the same dimension, yeah, they do not have those types of meanings.
Yes.
Any question? Just a simplified change of notation. Again, restriction number 1. What you observe is x0, your latents are xt, t is between 1 and t, the last one, we know that the last one is coming from a standard normal distribution. So I can simplify my approximate posterior as this one, just change up z to x, nothing more. We know that the approximate posterior is the distribution over latent, given observe, the latent are x1 to t, observe x0. If you use the Markov property, you have this factorization, and also for the joint. Previously for the joint, we have here z1 to t and x. Now I can simply write x1 to t, because x converted to x0, and then z's are converted to x. So this is the simplified version of the joint and the conditional approximate posterior. Restriction number 2. What was the restriction number 2? I myself also forget it. It's about the predefined linear Gaussian. What happened? Based on the restriction number 2, the distribution over x1 given x0 is using this kernel. You have a kernel, fixed kernel. Pay attention. You have a fixed kernel. It is not trainable. Then you use it to generate x1, then you use it to generate x2, then you use it to generate xt. And the kernel is this one. This is the another important point. The kernel is this one. It means that the distribution over the next in the sequence is the first one is a Gaussian. It is around, the mean is a scaled version of the previous one, and the variance is this term. Does it make sense for all of you? It is very important to understand this kernel. This kernel is adding noise. This alpha is less than 1. Pay attention. It's between 0 and 1. So in each sequence, you decrease the effect of your signal, your true data, because the information of the true data is coming from this term. Okay? Let's start from the first one. The Q of x1 given x0. What you observe, exactly the next one in the sequence, okay? Equals a normal distribution over x1 given, I select alpha to be 99, 0.99, okay? 0.99 x0 and 1 minus 0.99 the identity matrix, okay? You see, the information of what your data is coming via this variance. Through the sequence, you decrease the effect of your signal and add a bit of noise. Does it make sense how it works? Through the sequence, you are increasing the effect of your signal. Why you should increase the effect of your signal? Because at the end of this sequence, you want a pure Gaussian noise. If you have the effect of your signal at the end, it means that you do not have a pure Gaussian noise. It has the effect of your signal, your input pattern, your observed data. Does it make sense why they designed it as this one? And they add noise. They add noise because they want to go toward a pure Gaussian distribution. Clear? So, I have this formulation for the kernel. Okay. Yes.
The first layer, x0 is your data.
Yes.
And its dimensions or values of the feature space could be an arbitrary value, right? But the last layer, xt, you would like to achieve a normal distribution with mean of 0, right?
Yes.
But the transition between mean of your normal distribution is dependent on the xt minus 1.
Yes.
So in order to achieve the pure, very good normal distribution
At the end.
Yeah, at the end, if I just, for example, scale the input by a factor of, for example, 2, I have to increase the layers or capital T to achieve the same.
We have constraint about this alpha T and that large T. Because if this alpha T is near 1 from the lower values, then you can assume that the inverse diffusion process, the model, can be modeled as Gaussian too. So you are, because of a reason that we will see in the future, you are constrained to select alpha T almost near 0. It cannot be, for example, 0. We can easily put it 0 and we have a standard Gaussian noise. But that's not the option, because you want to design the inverse process, and the inverse process is Gaussian if this alpha T is almost 1, but from the smaller values. Then we have concept, and as a result, you will see. Any question?
Yes. So I was of the impression that alpha T changes.
Alpha T is a selectable parameter. It is not trainable. It's select. You select alpha T. You select alpha T to be 0.99.
Also, it's not like it's not a vector. It's just.
It's a scalar. Yeah, it's a scalar. So let's think of this formulation and think of reparameterization trick. We know that what was the reparameterization trick. We use it in VA. This distribution is this formulation, but I can change it as follows, okay? We know that I can write xt as square root of alpha t times xt minus 1 plus this term, and this term epsilon t minus 1 is coming from a normal distribution. This is exactly the reparameterization trick. Put aside the mean, it said that if you have a normal distribution with this mean and this covariance matrix, you can sample from a standard normal distribution and rescale it at the mean, you have exactly the same distribution. Does it make sense how it is reparameterization trick? So I have this formulation based on the fixed encoder. Now I can write the same for xt minus 1 for the previous one. Exactly the same, okay? And then I can replace xt minus 1 here from this part. I continue this procedure. I replace xt minus 1 here from this formulation. I have this one. I know that epsilon t minus 2 and epsilon t minus 1 are completely independent standard Gaussian samples. What happened? Just changing the order and formulation, I have this one. And here, pay attention to this part. I have the summation of two independent Gaussian, standard Gaussian noise. It is still coming from, because they are independent, their summation is easily calculated. You can calculate it easily. How? This to the power of 2, this to the power of 2, you sum them together and then take the square root, you have the variance and the standard deviation of the result. So, xt is a function of xt minus 2 with a new factor and also an added Gaussian noise. It is not standard, but you can change it to a standard using reparameterization again. How? I just apply reparameterization for this standard Gaussian. This part is the same. This part is reparameterization. It means that this epsilon star t minus 2 is a standard, but it is a scale. Why? Because it is not standard. It has this factor, so I use the square root of this function here to reparameterize it. Okay? Reparameterize it. Very interesting property. I can find the distribution of x2 given xt given xt minus 2 using this formulation. Do you follow the procedure? Is it clear how we reach this point? Yes.
Sorry, I'm not clear. It seems that alpha t is different from alpha t minus 1.
Yes, they are completely different. They are selected, but they are different, yeah. So, yes.
Sorry. So you can easily transform it down to a standard Gaussian if your alpha at that final step, if your alpha t there is 0, then it's
My alpha t is 0. Alpha t cannot be 0. They are constant. They are between 0 and 1, and they are almost near 1. This is the property needed for diffusion models. We will talk about why they should be that way. Just we are talking about. I should mention that alpha t are between 0 and 1 and cannot be 0 or 1. But now assume that they are between 0 and 1. They cannot be 0 and 1. So as a result, we have this formulation. If you continue this procedure, you will reach a very interesting point. I can continue this procedure. How? I can replace xt minus 2 with this formulation, something like this. Does it make sense? And continue this chain. Yeah. So now I can replace xt minus 2 and reach a point that xt is a function of xt minus 3. Is it clear for you? Just by using the same procedure. At the end, you have this formulation. You can relate xt for an arbitrary t to x0. What is the property of x0? X0 is what you observe. Very simple. X0 is what you access to always, because it's a sample of your training data. So, xt is a scale version of x0 and also some added noise like this. Can you understand how we can reach a standard Gaussian for x big T using this formulation? for a limited t. If this multiplication becomes 0, what happened here? This becomes 1, the complete. If this multiplication becomes 0, the other one becomes 1. So xt will be 0 times x0 plus epsilon star 0. If the multiplication is 0, it means that they are all between 0 and 1, so the multiplication is decreasing. If you have lots of them together, you may have something like 0. What is the distribution of this? Yeah, epsilons are always normal. I use the notation for the normal. So you have the normal. You have the standard Gaussian distribution for the last one, if that happens. Now we have some constants. So for this chain, we can derive the distribution for any steps in the chain given the x. So it's very, to some extent, relieving point, because you can sample from each of the nodes in your chain using your observed data. But you know that you should have access to the alpha values for different steps to sample from a specific step. It means that you should access to alpha 1 for this one, alpha 2 for this one, alpha 3 for this one, to sample from x to this point, because you need their multiplication here. Okay. So if we define alpha bar t, it is a very important definition. We use it for several times, so pay attention to it. Alpha t is the multiplication of alpha I starting from 1 until t. This is the definition of alpha bar t. Then xt is this formulation, and we know that it means that inverse reparameterization. Okay, inverse reparameterization. It means that the distribution over xt given x0 is this standard Gaussian. It means that you can easily sample from each step, each time stamp in your model given your observed data. Any question? Okay, notation update. Previously we have elbow of x, theta, and phi, but we do not have any phi anymore. You see that. This has no parameter, so you do not have it. Alpha t are defined scalars. They are hyperparameters of your model. They are not trainable, so your elbow is simplified as this one. And I again made a mistake. This phi is extra here. This is correct. Q distribution over x1 to t given x0. This is another problem. x0. This multiplication is correct, but we should omit phi. This is a new formulation for elbow. What happened? You do not have any training for the approximate posterior. Yes?
If that's the final equation, where there is no dependency of any one x1, x2, x3, x4.
This one?
No, the upper one.
Here?
No, the upper one.
This?
Yeah, so there is no dependency of x1, x2, x3 as such. So instead of hierarchical, can we just define one VAE wherein the root alpha t value will be, so root alpha t is like summation, multiplication of alpha 1, alpha 2, alpha 3.
Yes.
Just scalar. So even alpha t is a scalar quantity.
Yes.
So we, instead of defining n number of t number of VAEs, it's just one VAE.
It does not mean we have one VA, you know. It means that you can define the distribution over the t step if you have access to what you observe. We know that the distribution over xt given xt minus 1 is very simple. It is the kernel, okay? But we derive a formulation for xt given x0. Why? Because during the training you will see that we need this kernel. This is a new kernel built on top of your kernel, the kernel we defined for encoder part, okay? This is the kernel. It means that xt given xt minus L is very simple. But xt given x0 is not simple, but we derive a formulation for that. This one. You can sample from any step given what you observe. And this is important because during training you need them. Do you mean we have one simple VAE with one latent space? No, it is not that's the case, because here t can vary 1, 2, 3 until t, big T. Okay, uppercase T. You have all of them. Okay, so we have a new formulation for elbow. We use notation for elbow. It is not function of P anymore. This is the restriction number 3. The restriction number 3. What was the restriction number 3? Do you remember? Yeah, you want to design it so that the last one is Gaussian. We talked about how we can derive this condition. If you select alpha t so that because you select them, so you can select them so that this multiplication becomes 0, and as a result, p of xt given x0 is normal over xt. It means that although you have a conditional distribution, it is not dependent on your condition. Make sense? Yes.
The only way for that to hold is if one of the alpha t's is equals to 0.
Not necessarily, okay? If one of alpha, another option is you increase t and select alpha t is almost near 1. For example, just an hypothetical example. This number to the power of, for example, 300. All of them 0.99, but you have t equals to 3000. Sorry, 3000. This is almost 0. You need alpha t to be near 1 for diffusion process. We will talk about it later. Okay. So if I select them so that the alpha bar uppercase t is 0, then you have the property you need. So the restriction number 3 necessitates this equality to some extent. So independent of what you observe, the unconditional distribution over the last latent, even the conditional distribution over the last latent space, last latent vector is standard Gaussian, and this is what happened in your joint. Okay, in your joint you use this factorization p of xt, the multiplication of the other factors, and now you can replace it with a standard Gaussian here. Previously, we have p theta of xt, p theta, pay attention. What? No, this is the decoder. This is the inverse process diffusion. You know at the end, xt is a standard, okay? Independent of q or p, anything. xt is a standard Gaussian, okay? And I know that my model joint over all random variable in the hierarchy equals, using chain rule, equals p theta of xt times p theta of x t minus 1 given xt. This is what happened, yeah? I know that xt is a standard Gaussian distribution, so I can replace it. 0 and 1. Okay. What we have previously here was p theta of xt. It means that even the distribution over xt was parameterized by using this theta. Do you remember what we have in VAE for this term? We have p theta of z that, and then we think of PZ. This is exactly the last latent space, the last one. In the VAE, we have Z. At the start of VAE, we talk about prior distribution, parametric prior distribution, and then we said that generally we do not have parameter for the priors. We selected a standard Gaussian. The same thing happened here. The prior over the latent, the last latent, because we have several latent here. The prior over the last latent is exactly similar to standard VAE, vanilla VAE, which is the standard Gaussian. This is the result of your encoder. You design your encoder so that the last one is always standard Gaussian distribution. It is very important because it's first, it simplifies your joints. Second, it will simplify your generation after you train your model. Any question? Oh, we ran out of time. Sorry. I hope we can finish it in the next session.